Nick and the Netronome guys have been one of the earliest adopters and promoters of BPF as technology, offloading it onto their cards and doing all kinds of amazing things. And they didn't stop there. They didn't just make sure that their hardware works really well at BPF. The Netronome guys worked actively on tooling, and in particular BPF tool and things that provide introspection, as well as infrastructure for things like switch dev and improving support there. And if you look upstream, their contributions are all over the map. So look forward to Nick's presentation.
Hey guys, yep, that's working. So I'm going to talk about eBPF and switch abstractions. Now, obviously, that's actually quite an abstract title, but what I'm looking to do is basically move us towards proposing a path whereby we have a flexible eBPF-defined data path for switching in Linux. Now, this is very similar to things like what Will was talking about, but sort of Will's focus was really on the x86. Now, what we're actually going to be talking about more is heterogeneous processing. So how you can use Linux to basically control other elements, whether this be switch chips or in our case, the network processor on the NIC, and basically use that to move things a little bit forward in that space. So really what we're going to be doing is we're going to be combining CLS BPF, XTP, QDisk offload, and switch dev, all at the same time to create this infrastructure. And the first one I'm going to use as a demonstration is really the multi-host NIC. But there's a bunch of other applications as well out there. So the way we're going to run through this is I'm just going to quickly, first up, give a bit of background. Most of you will have seen this a few times already, so I'll try and keep this very, very brief. But a background of how the hardware works, because having that context is pretty important for all of this. And then after that, we're going to just go through a quick overview of the abstraction of what we're looking to do. And then we're going to run through what's currently upstream as of about 2 weeks ago. And then after that, we're going to go through next steps, which is actually the stuff that is currently being upstream. So I think Cooper posted some patches yesterday. Oh, great. They're already applied. So that's kind of what we're busy with right now. And then the final bit is the future work. And that's kind of when we get to what I've just described, which is actually having a fully flexible data path there. So just to give you guys a quick overview of the hardware. So what we have is we have basically a many-core, fully programmable network processor, which sits on a NIC. You've got up to hundreds of programmable cores down there, 8 threads per core. You've got up to 4 PCIEs, and you've actually got bizarrely up to 40 ports supported on one of the chips. So you'll see that's relevant for something I'm going to be talking about a little bit later, but it's basically a large mesh of small processing elements which all get put together in this sort of many-core architecture. The final bit is that we're also pretty low power, so 10 to 35 watts depending on the chip and the frequency. So just to give you a quick background on the data path. So the data path is pretty symmetric actually, whether you are on the receive or on the transmit path, whether you're coming from the file or the PCIe basically. The only bit that's really aware of the difference is the flow processing cores, the bit in the middle, because obviously you're going to have different functionality running dependent on where the packet has actually come from. And obviously you've got a few other accelerators like crypto down the bottom as well. And then because of the fact that we can handle things in an out-of-order pipeline, to be able to parallelize things and utilize our transactional memory as well as we can, we also have a reorder block. And this is the slide. I'm sure many of you have seen this slide about 5 times, so I apologize to those of you who have. This is just to give you a quick overview of the offload architecture. So basically, I think it's about 2 and a bit years ago now that Kuba posted the first patches for this. So this is what allowed us to actually offload BPF to the NIC. So what we did is we basically upstreamed an NFP BPF JIT into our driver. So the JIT is basically used like any other architecture's JIT. We compile the BPF bytecode to our NFP machine code. And as Dave alluded, through things like BPF tool, through some of the other infrastructure out there, you can actually inspect the assembler code you're generating and debug it and handle it like anything else. So just a quick background quickly, as NIC is a switch, there are 2 kinds of use cases we're seeing at the moment for the NIC being used in this kind of manner. That's the sort of multi-host case, and the other emerging one we're seeing is this quote-unquote multi-home case, whereby you have a significantly large amount of ports, way more ports relative to the actual PCIe of the host at the front of the NIC. This is effectively so people can start weaving their NIC into their CLOS architecture of their switches. So both of these cases lead to sort of an impedance mismatch, whereby you can have more traffic coming in on the one side than you actually have being synced on the other side. So that means you need to be able to handle things like a switch would normally do, things like quality of service, things like stats, to be able to debug issues. So that, and obviously forwarding, are the key things that you need to be able to really define as a switch. So just to give you a quick idea of the multi-host NIC today, there's a bunch of advantages to doing things this way, which is kind of the current way things are usually done. The hosts are effectively unaware of the configuration, so it means that it's easy to port things that you would use in other circumstances as well. But there are a few issues you run into. The first one is visibility. So being able to understand what's going on the other three hosts helps significantly when you're trying to work out, for example, why you've dropped a packet. Oh, it's because of the fact that this other host over there is getting a huge amount of traffic right now. So being able to have that visibility means that you can trust your programs and rely on the infrastructure you have in place. Second thing is there isn't really a way to offload Linux-controlled quality of service with this architecture, because really QoS QDisks are on the egress side. There is no representative to attach an egress QDisk to here on the L2 switch. So there's no way to really handle that at that level. And then the final thing is, obviously there's no concept of where you're attaching offloads. So if you're looking at things like XDP offload, which is something we worry about a little bit, you either have to have separate offloads for each one of the four hosts, or you have to somehow try and work out how they can share programs. So that means you're going to waste potentially code store in our case, or there could potentially be cases where people are using things like field programmable gate arrays. Then you can be wasting gates, wasting power. These are the kinds of issues that people need to consider. So, oh, sorry, I skipped a slide there. So what we came up with was using SwitchDev to kind of build this frame. So this is the first step of this process, is we build up this frame, and then once we've built up the frame, then we can start attaching things. So once we have this frame with egress representatives on the L2 switch, as well as an ingress representative on the actual PHY, and then the four normal host representatives, then we have a setup whereby we're able to attach QoS or QDisks to this point over there, and then also other offloads we can then attach to the correct points to attach them to. So next bit is just to quickly go through actually what's been done already as of 2 weeks ago. There are a couple of simple things we've done. So it was really, the first step was really having a simple set of single QDisks without a hierarchy attached to these representatives. So we added the sort of architecture of the representatives and with SwitchDev, and then we added in single QDisks. Now, this wasn't very fancy at this point in time. All of the traffic would be handled by a single QDisk, a single red QDisk at this point. So it could provide us with some features to help all the traffic when all the traffic was under the same basically priority for the host. But that was about all it could do at this point. However, this is the sort of the first step of what we needed as the overall frame. So to set this up, there were 3 key steps in terms of the implementation. First is the initialization, which actually happens when at boot time. So that would involve 2 steps, which is the app initialization and the vNIC allocation. And then we'd have the second step, which would happen when we enter SwitchDev mode. And then we'd have the third step, which is actually when we set up the QDisks. So in terms of the first step, which was the initialization, that's split up into 2 bits. First was the initialization of the app, what we call the app. So this is really actually our driver-specific piece of infrastructure. So we have this concept called the app abstraction, which allows us to reuse a lot of our driver infrastructure for different projects and different data paths. So for example, we would have things like NDO setup TC would do something different in this case than it would if we were running OVS via TC flower. That's the kind of thing we do. So a lot of the infrastructure code will look the same around those two cases, but the actual final function that's get called will be different. So it just allows a lot more reuse and a lot more configurability. So that gets set up first. First, we need to set up the app structure for this actual use case. And then the second thing we need to do is we also need to set up a structure called the NFP ABM link, which is something which gets used for hooking a lot of the infrastructure, and we'll see more of that over the next little while. There's also a bunch of checks which are quite important to do at this point, otherwise you're going to have some weird gotchas. First thing is you need to make sure that you actually have enough MAC addresses assigned to this device, because of the fact that you've got a bunch of different hosts you're attached to. So you need to actually have enough Macs to be able to handle what you're meant to be doing. Second thing is you need to ensure you start the NIC in legacy mode, because at the moment, obviously, there might be use cases where people are not yet able to use this type of switch dev abstraction. So you want to start the NIC in legacy mode. You don't want to start it in this kind of mode and then break someone's orchestrator. And the third thing is you also need to make sure that the MAC state doesn't follow the ports, because if you put a port down on one of the 4 hosts and that takes your MAC down, then you've hosed the other 3 hosts. So there's just a bunch of really simple checks, but things you need to do at this point. Then the next step is actually entering switch dev mode. So this really revolves around the concept of spawning the representers. So this involves actually creating the required net devs. And then one of the important things to note at this point is that the actual physical port representative is only going to get a single queue because of the fact that you aren't hooked up to an actual end device. So that's just an important gotcha there as well. And then you're going to link up those net devs to the representers. Once you've linked them up to the representers, you'll then attach them to this ABM link structure. And then once you've done that, once you've got all of this set up within the driver, you will then actually initialize the firmware. And so then at this point, you've now basically set up your frame. Your NIC is ready. Your NIC is set up in this switch dev mode, and it's ready to be able to have Q disks attached to it. And the final thing is just to attach the Q disk. Now, in this first case, this was actually a pretty simple setup. You just had a single red Q disk which you would attach, and it was pretty useful because of the fact that suddenly when you do this, you have all of the TC stats available as well. So it's super useful for IDing things like microbursts or other issues within the data path. So the next step we then had was actually now extending this a little bit further. So what we want to do in this section is really look at generalizing the QDisk offload, which is, again, this is part of the patches that are going up at the moment. This needs some structure changes in the NFP ABM link structure, as well as generalizing this QDisk structure. Now, once we've done that, then we have suddenly this motivation to add in basically classifiers. And we'll talk about that and describe some of the simple stuff around adding in classifiers there, and then just very quickly jump through sort of how that architecture hooks in. So what we have is, before we basically had this set up here, so in your ABM link structure, which is kind of the structure which controls all of this setup, you would have this single structure for the red Q disks, and in there you would just have a very simple handle and some stats. So this obviously is not a scalable model at this point in time. So what we've done is we've created something which is a bit more scalable. So effectively you have a root Q disk, and with that you have the whole hierarchy of Q disks, and you have multiple types of Q disks. This is a dummy structure. Obviously there's going to be more and more Q disks added to this, but this is just like as a start, just to show how the structures would look. And it's important to note, obviously you now have children and a whole hierarchy. And so you're keeping track of this whole hierarchy. And by definition, you then also have stats for this whole hierarchy, which is actually already found itself to be incredibly useful in environments where we've been debugging burstiness issues. So once we have that done, we suddenly have this ability to have different queue disks for different types of traffic. And that means we suddenly need to have a classifier. So if we want to be able to use this to the fullest, we need to have a classifier attached to the front of those egress representers, because having that classifier will then allow us to be able to steer traffic as we want it to be steered. So what we did then was we, just as a very simple first case, is we just added a very simple U32 classifier. This is just simply for a easy case where we're just using a DSCP map to be able to steer traffic with respect to the priority that's been given. But this is obviously a very first step, and really what we want to get to is what I'm now really looking to cover in the next section. This is what we're now getting to. So once we have all of this complete and upstream, we really have the foundation. That's kind of the baseline for actually building the stuff we want to have. So then we have the framework, and now we can start attaching things to it. So what we need to do is there's a couple of minor changes we need to make within the BPF JIT and within our sort of BPF infrastructure. And then there's one slightly larger sort of driver, basically architecture change. So that's a bit more of a significant one, but we have those three things to do really. And then we are ready to roll in effect with making something which is getting much, much more complex. So in terms of the firmware and the JIT, at the moment, the way our JIT works is we effectively have a point in the NFP, in the code store, where the programs get put. So if you are writing a BPF program, you write your BPF program, gets compiled down into NFP assembler. Our driver then takes that NFP assembler and it puts it in a very specific location in the NIC, and I will always start at a specific offset. Now what we're doing is we're adding in a much more flexible way of doing this, so that you effectively have a very simple jump table which tells you which ports require which programs. So you have a set of programs which sit there. Because of the fact that many programs could potentially be shared, and the example we'll be looking at later will use a lot of shared code, this will allow us to significantly save on code store. And also by dynamically loading helpers, we won't waste our code store for helpers we won't be using. So by setting this all up, we give ourselves the best chance to be able to offload as much as we can. So we have about 16K worth of code store here, which is available for this. So that allows us to offload a pretty significant amount of code. The final thing to note is also, I've just put a little note here, the pre-classifiers, which I haven't actually spoken about, are a bunch of sort of small hardware classifiers, which do a lot of the same jobs actually that Saeed and PJ were talking about yesterday. They kind of give us offsets in terms of where the packet different headers start, and add a bunch of metadata. And the other thing they also do is they load balance the packets across the flow processing cores, so that we're able to actually load balance the packets at that level. And what we can potentially do with these is if we want to isolate specific flow processing cores to specific hosts, we can use these to basically partition the NIC if that becomes something which in the end of the day we decide is useful. And finally, this then gives us all the infrastructure we need to start adding in CLS BPF, apart from one thing. The one thing we're then missing is that at the moment, I remember the app abstraction thing I was describing earlier. At the moment, BPF is its own app abstraction. So it is effectively one of these quote-unquote flavors we have within the NIC. So you can be running BPF, or you can be running OVSTC, or you can be running the initial version of the switch dev offload with adaptive buffer management we've been talking about here. However, and I think this is part of the sort of progress of BPF, we're now kind of moving beyond BPF just being used for sort of load balancing or DDoS or these very, I don't want to call them simple, but these very specific use cases. What we're now starting to see is we're using this as a tool. We're using this as a tool to implement other things, to use things in a much wider basis. So what we need to do is we need to, and this is going to be a pretty painful piece of work for some people, I suspect, is actually move the app abstraction layer out so that BPF is no longer part of the app abstraction. BPF is actually part of the core infrastructure we have within our driver. so that it can then be reused for different things, and especially as things like OVS move towards BPF-based data path, there will be all kinds of places where we're using this. And if we really get to the final objective, which we'll get to in a little bit, of actually having this as a fully BPF-defined sort of data path, then we're going to get to the point of needing to use this in many more places. So so that gets us to the point of having multiple queue disks, having CLS BPF there to act as a classifier to decide which queue disks to use for different traffic as it comes in. We have the switch dev architecture set up so that we have different representatives for different logical ports within our NIC. And now we need to add in the last bit of this puzzle, which is actually starting to add in XTP. So there are a couple of problems that are these are not insurmountable problems for this use case. And they're not insurmountable for the very specific reason that we now have all of these representatives. The first one of these is obviously XTP is an RX exclusive hook. You can't run XTP on TX right now. That's not something, and there's good reasons for that. So because of the fact that we've set up this architecture with all these points, we can actually hook in now XTP on the receive side of our switch ports, of our logical switch ports for each one of the multi-host NICs. And by then using things like redirect there, we suddenly have a forwarding plane defined. So we're actually able to define our forwarding plane using XTP. And so that's a pretty powerful thing to be able to do. Now, the second challenge we have in this case is obviously now we have our support, and we've got a sort of uniquely good architecture to be able to run this kind of thing right now. But other heterogeneous architectures, the support for this is nascent, but this is something which people are working on. So I mean, like this stuff that I think PJ mentioned yesterday with more flexible NICs coming in, which can potentially do some of this kind of work by having a simple JIT which allows them to offload these types of programs could potentially be very powerful. And having that heterogeneous support is always going to be great. And the final thing I wanted to mention there also is security. Now, this ironically this won't be a problem for true switches. For true switches, you have your control CPU, which sits there on the switch, and that can be the thing running all of it. But if you have a PHY port here and you're hooking XTP programs onto it, you've got to trust the other 3 hosts that are sitting there with you. Because if you can't trust them and host 0 decides that he's going to take all the traffic actually meant for host 3, then you obviously have some significant problems. So this has to be in a trusted environment. Now, there are a couple of ways around this. The first one is the one which we described with, actually I'm going to just keep it there, with it being a real switch. And the second one is obviously if you're using this with bare metal NICs. So bare metal NICs have their own ARM system sitting there, and they can then control this. But a lot of places we're seeing this kind of architecture, there is this trusted environment. Like everyone is able to trust everybody else involved here. And if worst comes to worst, you can always find a different way to be able to add that in there. But that's not something we've really thought about far enough to be able to come up with a different proposal there at this point in time. And also now being able to add in, so I think David spoke yesterday about things like fib table access. Being able to add that kind of stuff into this, suddenly you have your whole switch architecture there and you have everything defined you need. So now you have a BPF-defined data plane that's able to give you quality of service, stats, and you're able to redirect things and define the forwarding plane with BPF. And that's really where we were trying to get to. Now, we're about a third of the way there with that. There's a lot of work to be done before we get there. But it's something which I think we wanted to share and start moving forward with the community so everybody understands where we're trying to go with this stuff. And obviously that then means that people will have more context when they start seeing stuff moving forward. And I think that's kind of important. So there's obviously going to be more stuff coming here, and there's going to be a bunch of issues and a bunch of questions, but that's just to give people an idea. Now, Kuba's going to talk. I'm going to give him a shameless plug for his chat tomorrow at the micro conference where he's going to be talking about heterogeneous architectures for BPF and trying to move this to more different types of architectures like switches and other types of things that are out there. So I think that's a really important thing to take further. And finally, I just wanted to give credit to the team. These are the guys doing the real work. I just get to talk and smile. So, oh, and finally, I wanted to also thank the conference staff because they're the only reason I have a clean T-shirt today. Okay. That's it.
Thank you. So that pre-classifier is ASIC logic?
Yes, we have a set of 48 to 96 small ASICs, which basically sit as you come in right by the PHY and spread packets around. And they add a lot of the logic that, like Saeed was talking about yesterday, where you have the basically the pointers to the right places in the packet.
I see.
Yeah, he knows more. Trust him more.
This becomes relevant when you start talking about stuff like the XDP hints, like
Yes.
the metadata that the preclassifier outputs. It's in itself so compressed and hard to use. Some firmware engineers actually reclassify the packets themselves because like just unpacking the structure is like the hint is so complicated in its own. It's like
Yeah. Thanks.
Any other questions for Nick? Okay.
I'm gonna
oh,
get away.
wait. Hey.
Oh, I thought
You
I got
slipped
away
in there. You almost escaped.
Yeah, I thought I got away.
If I got one of your first slides right, the chip supports like 40 ports, right?
One of the chips has a huge amount of ports on it, yes.
And are you planning to support allocating them dynamically to each host? Like your examples had only one port allocated to them.
So by this I mean physical ports. So there's actually, like, you can have 40 input ports,
Physical, okay.
like a switch tile type thing. Because there are use cases where we have applications which have a huge amount of very small input ports, like we'll have 40, 100 meg ports coming into the one chip. But that's also relevant when we're talking about cases where suddenly we have 4 or 8 25 gig ports coming into one device because people are hooking their NICs into a huge amount of switches in their closed network. That's more, it's on that side where I was describing this.
And on the host side, would we have more ports? Because it seems it would be interesting to allocate these ports directly to our guests, for example.
Are you talking about, so you're talking about if you have a virtualized case?
Yeah, SRV or something like
Okay,
that.
so I mean, there are a bunch of VFs there as well. So at the moment, I was only describing physical functions. But you could potentially hook in SRV on top of this, yes, and then attach that to a bunch of VFs. There's no reason why you couldn't do that.
So why are you only supporting red as a Tutor flirt? We can do better than that now.
Yeah. No. Let's be clear. Yeah, that's definitely not the end game. We started off with red because there were some very specific applications for which it would be very useful where we're dealing with customers. In fact, multiple customers are using things related to red. We also have cases like G-Red, where you've got multiple different basically queues which are all red, but with different thresholds and different actions, like drops or marks with ECN marking, that kind of thing. There's also other QDisc we'll definitely be looking at, as we're going forward into the future, like token bucket type stuff.
So I have a question about those specialized classifiers that you mentioned. So the data is produced out of those metadata, the hints, whatever you call it.
Mm-hmm.
Do you expose it to the eBPF program? Is the eBPF program aware of those?
Not right now, no.
Okay.
No, so we're not actually using those, and that's why something like the XTP hint stuff, which the guys are describing, would also be useful for us, even in the offloaded case, because we could then actually use that infrastructure and all that stuff we have there and reuse it in this way, which is something we don't really do today.
Okay.
Now we do, there's some ways we maybe use it, but it's not really used today. We could certainly do more with it.
Okay. Thanks.
Ready?
So what application manages this switch?
Say that again, sorry, I didn't catch that.
Which application are you using to manage to orchestrate all this?
So to orchestrate today, or so today, most of the multi-host NICs just work through a simple self-learning L2 switch. So effectively, it's just a very simple MAC learning switch, which just switches the packets. That's what's happening today. Now, over time, the whole point would be to be able to use XDP as a forwarding plane. And then to do that, that would obviously be done whatever the host is using to control the XDP programs. So as of today, it's a very simple L2 MAC learning switch, just punts the packets according to the MAC address. And then in the future, that would be for our customers to decide. That's not for us to decide. The whole idea is we're providing this thing, and it's software defined, so that our customers are able to write their software.
Anyone else? Thank you very much, Nick.
Thank you, everyone.